Let's jump right into this explainer. Today, we're uncovering the absolutely stunning visual math behind something called Cantor bubble Julia sets. Now, if you've ever looked at a fractal, you already know they can be incredibly complex, right? But what we're looking at today is a very specific, totally mind-bending class of fractals that mathematicians have recently been hunting down and analyzing. It is seriously fascinating stuff.
So think about this. What happens when you slightly break a perfect mathematical equation? You might think it just stops working, right? Like if you have a perfectly balanced equation that draws a smooth, unbroken circle, and you introduce a tiny, almost microscopic mathematical error, you'd probably expect the circle to just get a little wobbly. But in the realm of complex dynamics, oh no. Singular perturbations don't just wobble the circle, they act like a literal mathematical butterfly effect. This beautifully illustrates exactly what happens. Tiny, specific changes to simple equations absolutely explode into infinite chaotic beauty. By just adding a tiny fraction to a polynomial, the boundaries of the shape shatter. And I mean, they don't just break into a few pieces, they fracture into an infinite landscape of swirling, endlessly repeating structures. It's like a giant puzzle exploding into a million perfect pieces.
Now don't panic about the math here. We're going to walk through this step by step. Our agenda for today covers perturbing the Julia set, defining the Cantor bubbles, the generation criterion, high-period attracting cycles, Hausdorff dimension 2, and finally, the perfect round bubbles.
All right, starting off with part 1, perturbing the Julia set, the mathematical butterfly effect. Normally, a Julia set is basically the boundary line between points that fly off to infinity when you run them through an equation and the points that stay safely trapped near the center. For a simple equation, this boundary is just a perfect unit circle. But take a look at how the Devaney-Murata family equation totally upends that. It fractures that once simple circle into isolated, floating islands. By introducing a pole, which is a specific type of singularity, into the equation, the math draws this incredible, complex map. All those little yellow dots are completely isolated from the main outer wall. The simple circle is just gone.
It's a perfect visual representation of chaos theory. A tiny shift creates a structure that literally cannot appear in older, simpler models. Take the older Macmillan family model, for instance. Perturbing that math just creates a series of nested rings, kind of like a bullseye. But this Devaney-Murata perturbation, it does something entirely different. It creates a wild mix of disconnected curves and infinite points. We're talking about an entirely different species of mathematical beast here.
Moving on to section 2, defining the contour bubbles. What exactly are we looking at?
Well, mathematicians needed a precise way to classify this bizarre hybrid. Because, it wasn't exactly a solid shape, but it wasn't just scattered dust either. So to put their formal academic definition into a more physical metaphor, I want you to imagine a bizarre universe on a 3D mathematical canvas, a Riemann sphere, that's governed by 3 strict rules.
These fractals are basically a mixture of countable bubble outlines and uncountable mathematical dust, all floating in a single, infinite, interconnected ocean. Let's break that down. First off, you have solid, closed loops. Those are your bubbles. Second, you've got a completely disconnected spray of infinitely tiny, isolated dots. And third, the space around all of this, the background, is entirely connected. It is one single ocean that wraps around every single bubble and every single speck of dust.
Let's zoom in a bit. You can clearly see the distinct, separate bubbles and the single, unbroken yellow background that flows around all of them. Notice how no 2 black boundary lines ever cross or touch? Every single yellow bubble is perfectly isolated, sitting entirely on its own inside that vast, connected, bright yellow ocean. That right there is the visual signature of a Cantor bubble Julia set.
Okay, section 3, the generation criterion. Let's unpack theorem 1.1.
Now that we know what they are, how do mathematicians guarantee they'll actually appear? You can't just throw numbers at a wall and hope for the best. This is where theorem 1.1 comes in. It's the precise recipe ensuring a Cantor bubble Julia set will generate instead of just a connected shape. Alpha 2 component is basically just a stable region, like our yellow ocean or the yellow inside of a bubble. The theorem states that if you have 2 of these stable regions, and one of them completely dominates the map while the other doesn't, and all the mathematical tension, the critical values, are trapped inside these 2 areas, boom, you get Cantor bubbles.
And here is that exact recipe in action. By having one super-attracting fixed point and another critical point just escaping to infinity, we get these isolated floating fractals. This specific shape comes from a cubic polynomial. The math is literally pulling the boundaries apart into this beautiful, disconnected, floating archipelago, all because the critical values are perfectly distributed according to Theorem 1.1.
Which brings us to Section 4, High Period Attracting Cycles, expanding the rules.
Theorem 1.1 was mostly about simple one-step stability, but what if the points inside bounce around in a longer, way more complex cycle of 2, or 3, or 100 before finally settling down? On the left, we have a true Cantor bubble set, but on the right, if the math parameters change even slightly, the bubbles merge into a connected basilica structure. It really shows how delicate this balance is. To get the true bubbles on the left, while dealing with multi-step cycles, researchers had to use advanced topological tools. They literally proved that you can generate super-attracting cycles of any given period without the boundaries crashing into each other, like they do on the right.
All right, Section 5, Hausdorff Dimension 2, a paradox of disconnected sets.
Prepare to have your mind completely bent by Theorem 1.3, which explores how we actually measure dimensions. We aren't talking about standard 3D space here. We're talking about Hausdorff dimensions, which measure how densely a fractal fills up its space. Usually we think of disconnected dust as having 0 or 1 dimension, right? But mathematicians prove these Cantor bubbles can be so densely packed they actually achieve a 2-dimensional Hausdorff space. Imagine taking a piece of paper, cutting it into infinite disconnected pieces of dust, but that dust is so unimaginably compact and complex that mathematically it still behaves like a solid 2-dimensional sheet. It's an absolute paradox of geometry.
By using a wild technique called quasi-conformal surgery to glue different polynomials together, they forced this chaotic dust to paradoxically take up 2D space. The researchers literally cut a cubic polynomial that possessed a full 2-dimensional dust cloud and mathematically stitched it to a quadratic equation just to ensure the bubbles formed. They basically built a mathematical Frankenstein's monster just to prove that 2-dimensional Cantor bubbles can actually exist. Mind-blowing, right?
Finally, Section 6, the perfect round bubbles, smoothing the chaos.
So, after creating these wildly dense, chaotic shapes, researchers asked a crucial question. Can we smooth it all out? Can we take these infinitely jagged borders and map them onto perfectly smooth circles? The formal term they use here is quasi-symmetrically equivalent, but basically, they were asking, is there a mathematical map that allows us to stretch and warp this crazy fractal space until every single one of those infinitely complex, jagged bubbles becomes a perfect, smooth, round sphere? The answer? Yes! If the critical orbit doesn't accumulate on the curves, the set is quasi-symmetrically equivalent to round bubbles. That means the chaos is mathematically smoothed out. As long as the most chaotic forces in the equation steer clear of the boundary lines, mathematicians can use a principle called Bonk's criterion. This proves that underneath all that jagged fractal complexity, the fundamental structure is essentially equivalent to a universe of perfectly uniform, smooth circles.
So what does this all mean? Well, if just a tiny microscopic perturbation of a simple equation yields infinite dimensional oceans of perfect fractal bubbles, it really makes you wonder. What infinite, undiscovered shapes are still hiding inside the equations of our universe? The math in this paper isn't just about drawing pretty pictures. It's about defining the absolute limits of topology and complex dynamics. It proves that within the simplest equations, entire chaotic, beautiful, perfectly structured universes are just waiting for the right perturbation to bring them into the light.